Okay, y'all, so today we're going to be going over exam 2023, question 1, and this is going to be really a voltage drop problem going in a circular, electric field. So here it says, and inside of a transformer core, there's an electric field that is given in cylindrical coordinates, very important, as E is equal to phi hat rho cosine omega t. Find the voltage drop VAB between points A and B by using paths as indicated below. Okay, so point A is on the x-axis, point B is on the y-axis, so we're given this circle of charge, really, or I guess an electric field, and it's asking to find the voltage drop in different paths. So, first thing here, part A, we need to figure out what path we're on. So we're going the counterclockwise direction, so we're going to label that from A to B like this. And now, how do we get voltage drop from electric field? Well, V is going to be equal to the integral of E dotted with dr. Now, in cylindrical coordinates, using, again, note 6, dr is going to be equal to what? Dr is going to be equal to rho hat d rho plus phi hat, which is what we have, rho d phi plus z hat dz. And if you're going to take the dot product between two functions, the functions that get output are only the ones that share the common unit vector. So if E is getting dotted with dr, this is going to output a phi hat, right? Because our E component only depends on phi hat. So that means what do we get? Well, we get rho times rho cosine omega t. All right. So what does that really mean, though? Well, that means we end up getting what? Rho squared cosine omega t. Perfect. So that is our E dot dr. Now, VAB is equal to, what is our new d phi? Or what are we integrating with respect to? Well, it needs to be d phi because right here we're using this unit vector rho or phi hat. So we get E dot dr is equal to this times d phi. We can't forget that. So it becomes rho squared cosine omega t d phi. And now since we're integrating over the phi, what are our bounds? Well, our bounds, remember in the xy coordinates or in the xy plane for cylindrical coordinates, we are changing with respect to phi. So we're going from, let's call this 0, we're going to the y-axis, which is pi over 2. So it becomes 0 to pi over 2. And think counterclockwise, this is going to be positive for the unit vector or unit circle. So we don't have any negatives, it's just 0 to pi over 2. Now, what is rho in cylindrical coordinates? Well, rho is our radius. And what is our radius in the context of this problem? It should be a. So a is not rho, or a is not phi. So we can move that on the outside. It's technically a constant. So it's a squared integration from 0 to pi over 2 cosine, again, cosine omega t. Does that depend on rho? No, it doesn't. So let's also move that outside. What are we left with? Just d phi, and that means we have pi over 2, right? So we have pi over 2 times a squared cosine omega t volts. That is our voltage drop from A to B going in the counterclockwise direction. Now part B, we're now going, instead of the counterclockwise direction, we're going the clockwise direction from A to B. So now we're starting at 0, and we're still going to end up at pi halves, but Now we're going in the negative direction for unit circle. So what is the integration going to be? From 0 to, well, it can't be pi halves again because that's positive. So negative, this is going to be negative pi over 2. This is going to be negative pi. That means this is going to be negative 3 pi over 2. So we're integrating from negative or 0 to negative 3 pi over 2. And just the electric field doesn't change and the dr doesn't change, so we're still integrating a squared cosine omega t, and we're integrating d phi. The e dot dr doesn't change, only the bounds of integration change in this case. So now what do we get? Well, we get negative 3 pi over 2 a squared cosine omega t volts. And this is equal to the voltage drop from A to B in the clockwise direction. Now it gets a little bit weird. Now we're asked for part C, what if we go in lines? What if instead we go from A along the x-axis to the origin? So we're going in this kind of direction. And then from the origin to point B. Okay, so now this changes our dr, because now dr is not not in cylindrical coordinates per se, but we're changing the path that we're taking. Before, dr was really just like, or actually we can just say dr is now d rho, right? Because we're changing our path not in d phi, or yeah, we're not changing with respect to d phi, we're now changing it with respect to d rho. D phi is not, or phi is not going to change with time, or I guess time. It's our radius is now changing. The path that we're taking is different. So now, what does that like? I hold on. I'm trying to explain it in a way that y'all can understand here, because it can be confusing. This is definitely pretty confusing, I would say. What is E changing with respect to? Well, E is a circle, and if it's an induced electric field from a core, it should be changing, something like this. It should be going in a circle, because again, we have cosine omega t, so it's changing with time, and it's doing this sort of thing. It's spiraling in a circle, going counterclockwise. Now, what do you notice about the path of integration, or the path that we chose? Well, the path going from A to 0 at this specific point, at A, we notice the paths are perpendicular. E is perpendicular to the path that we chose. What does that mean for our dot product? Well, that means our dot product is 0, because E dot dr is the same as the magnitude of E times the magnitude of dr times the cosine of the angle between them. And if the angle between them is 90 degrees, cosine of 90 is 0. So because the path we chose and the electric field vector that we're given are perpendicular, this means the voltage drop between the 2 points has to be 0. Now, you could make the point, how did I know that the electric field vector is going in a circle? Well, of course, they've given it to us, right? They've given us that the electric field is in cylindrical coordinates, and it's varying with time. It's a cosine function, right? Cosine functions, they're periodic, and it has an amplitude of rho. So it's actually giving it to us. It's telling us the electric field is a circle with amplitude rho, or radius or rho. So in our case, in this specific problem, we can say, yes, we know the electric field vector is perpendicular to the path that we chose. So it's 0. Hopefully that explanation was okay. If you have any questions, because it can be confusing, I'm telling you right now, it is confusing. So if you have any questions, please reach out to me. But other than that, this is how you do the problem. Again, this is 30 points, so you would give 10 points per problem per part, hopefully. So you should be able to get this part A and part B done pretty quickly, I would say. Part C is where you have to, it's a theory check. So just to make sure, if you want and you're not understanding this, maybe you can try and think of it a different way. Try and think of, okay, well, I don't really have much to go off of here. What does E dot dr mean? Well, E dot dr is the magnitudes multiplied times the cosine of the angle between them. Maybe that could be something we look at. And there's just a couple of possibilities you could go through whenever you're taking the exam, and you can definitely get stuck on a problem. But if you get stuck on a problem, you have to move on because you don't want to waste time. Anyways, hopefully this helped. Yeah, I don't want to give y'all like life advice for real. Let me know if y'all need any help. Thank you.